In this week's video, we will be discussing freezing point depression and boiling point evolution. We will be doing two problems. The first problem states, for a solution of potassium chloride in 250 grams of acetic acid, with its Kf value given, the freezing point is 13.34 degrees Celsius. If pure acetic acid freezes at 16.60 degrees C, what is the mass of the dissolved KCl? First thing that we need to do is look at our freezing point depression equation. That is delta T equals Kf times the molality and our Van't Hoff factor, which is I. For our potassium chloride, because it is a soluble salt, it is going to dissociate into two ions. So for our I term, we need to consider two ions. This will come into play when we input it into the formula. So now we must determine our change in temperature. This can be done by taking the difference of the two. So our change in temperature will be equal to, and while many of you are used to final minus initial, that will provide a negative answer, and we cannot have a negative molality. So we will take 16.60 degrees C and subtract our 13.34 degrees C, and this will give us our temperature change. That value is 3.26 degrees C. This shows that our temperature went down by that 3.26. So now, because we have a Kf value of acetic acid and we have our Van't Hoff factor for potassium chloride, we are able to calculate the molality of our solution. This is done by saying that 3.26 degrees C, our temperature change, is equal to our 3.90 degrees C per molal. This is our Kf term from the problem, times our molality, and then times our two ions, because this is a dissociating solute. If we put all of this information into the calculator and solve for molality, you will get a value of 0.418 moles of our potassium chloride per kilogram of solvent. In this reaction, we actually don't have 1 kilogram of solvent. We only have 250 grams. So we are going to multiply our denominator by 0.250 kilograms of solvent in order to determine the number moles of our solute. So we can cancel out our units of kilograms of solvent. This will be put into a calculator. You will receive an answer of 0.104 moles of potassium chloride. Then what we can do is take that number of moles of our potassium chloride and we will multiply it by its molar mass. So in this case, the molar mass of potassium chloride is 74.548 grams per 1 mole potassium chloride. You put this into the calculator, you will receive an answer of 7.75 grams of potassium chloride. So if I had 7.75 grams of potassium chloride and I put it in 250 grams of acetic acid, we would get a freezing point to depress down to 13.34. For our second problem, arrange the following aqueous solutions, each 10% by mass, in order of increasing boiling point. We have glucose, potassium nitrate, and sodium carbonate. the first thing that we need to do is look at our boiling point equation. That is, our change in temperature is equal to Kb times our molality times I. But seeing that we have the aqueous solution, they will all have the same Kb term. So if we eliminate that, we can decide that our change in temperature will now be proportional to just two of our variables. So our change in temperature is going to be proportional to our molality times our Van't Hoff factor. So the first thing that we want to do is look at the Van't Hoff factor for all three of our solutes. Our glucose is a non-dissociating solute. It stays as one particle. So our C6H12O6 will have an I term of 1. For our potassium nitrate, this is a soluble salt. It does dissociate into two parts. In this case, those parts would be potassium plus and our nitrate 1 minus. So we would get a Van't Hoff factor of 2. Finally, for our sodium carbonate, it is going to dissociate into three parts, 2 sodiums and the carbonate anion, so you would get an ideal Van't Hoff factor of 3. The other important part of this is going to be our molality. Molality, once again, is equal to moles of solute over kilograms of solvent. So let us go and start with our first solution. Percent mass, by definition, is the mass of our solute over the total mass. So if it is 10% by mass, we will have 10 grams of our C6H12O6 divided by 100 grams of total mass. But in this case, 10 of those grams are our solute. So we could say 10 grams plus the remainder being water, which is our solvent, which is 90 grams of our water. Now we need to convert our grams of our solute to moles of solute. So we're going to take the 10 grams of the C6H12O6 and multiply it by 1 mole over the molar mass. So we can say 1 mole over 180.156 grams. The grams and grams will cancel, and we will be left with 0.0555 moles of our sugar. So now we must go and divide by our 90 grams of water, but it must be in kilograms. So we can do this by dividing by 0.090 kilograms. You will get a value of 0.167 mole particles. So now, let us go and do the exact same math for our potassium nitrate. So we have our 10 grams of potassium nitrate. We are going to need to multiply it by our molar mass in order to get moles. So we can say 1 mole over 101.108 grams. This will give us a number of moles of 0.0989 moles of our potassium nitrate. We're going to divide by our 90 grams. So in this case, it is going to be 0.090 kilograms. And you'll receive a molality of 1.10 molal KNO3. But remember, this dissociates into two parts, so we must multiply it by 2 in order to get the number of particles. So if we do that, we will get a number of particles being 2.20 molal of particles. This does take into account our potassium nitrate dissociating into two parts. Now we must go check our third solution. Our third solution in this case is our sodium carbonate. And we will go and have our 10 grams of our Na2CO3. We are going to multiply that by 1 mole over our 105.99 grams for our sodium carbonate. And this would give us a value of 0.0943 moles of our sodium carbonate. If we divide by our kilograms of water, so 0.090 kilograms, you'll get a value of 1.05 molal sodium carbonate. We must multiply it by 3 to account for the Van't Hoff factor. So we will now include the multiplication of the 3 particles, and you will get an answer of 3.15 molal particles. So now the question becomes, which one would have the highest boiling point? So as we know, if we put more solute into a solvent, the boiling point will increase. So we have the fewest number of particles giving us the lowest boiling point. This would still be higher than the pure solvent itself, but it does give us the lowest change. Then we will see for our potassium nitrate, because our molality of particles is the second highest, it would be the one in the middle. And finally, with our sodium carbonate, we will have the highest change because it has the highest number of particles. In these two problems, you have seen how the addition of a solute to a solvent can change the boiling point and freezing point of a solution. Good luck.